consider this sketch of the polynomial y equals p of x. You can see I've labeled these points that are the x-intercepts, the points where the graph crosses the x-axis. So these points represent x values that are roots, otherwise called zeros, of the polynomial. And what I want you to notice is that between each successive zero, or x-intercept, there is going to be either a positive or negative y values exclusively in that region in between. So if we look at the graph to the left of the first zero, the first x-intercept, since that part of the graph is below the x-axis, it indicates the y partners on that portion of the graph are negative. So in that region, the y values are negative. But look at the values of the y values between the two intercepts beside that to the right. Those are all positive because they're all above the x-axis. Between the next two zeros, all the y values are negative because the graph is below. Then we have positive for the graph above, and then again positive for the graph being above because that was just a kiss at that intercept. Okay, so this fact that we are either always positive or always negative between successive zeros or roots, it's validated by something called the intermediate value theorem. The intermediate value theorem says basically if the y values p of a and p of b, where p of x is our polynomial, if the y values p of a and p of x have different signs in that situation, that implies that there has to exist at least one x value, x equals c, such that p of c is equal to 0. In other words, you're going to have to cross the x-axis someplace because a polynomial is a smooth, continuous curve. So if you have y partners that are negative and then y partners that are positive, different signs, somewhere in between on the x-axis, somewhere in between A and B, you're going to cross the x-axis. So you're going to have a root C, in other words, an x-intercept. That's validated by the intermediate value theorem.